So our final speaker of the afternoon is Hilary Greaves from Oxford, who will be talking about a classical analog of CPT.
Okay, so I have a few apologies to make. The first is that this isn't the advertised talk, but if you read the paper that I posted on the conference website, it's very closely related to this one, so that'll be fine anyway. The second apology was going to be that I'm not going to talk about quantum field theory. I'm going to talk about classical field theory, but since not talking about quantum field theory seems to place me in the majority today, I won't bother. And then finally, some of what I'm going to say is going to be relatively mathematical, so I was in two minds about whether to give this talk, because when I'm sitting in the audience, I find it quite difficult to absorb very mathematical talks, and I don't find that's the most helpful format for conveying mathematical ideas. But then eventually I decided I couldn't resist it, because it's quite a rare opportunity here to speak to an audience with as much technical expertise as this one. And the project that I'm embroiled in is one that's putting me right at the edge of my mathematical ability. So I'm really quite keen to get some feedback. So I want to, in addition to giving the overview of what I'm trying to do and why I'm trying to do it, I want to put enough of the technical stuff out there so that those who do know more maths than me are in a position to say useful things. Okay, so I'm talking about the CPT theorem. This is a theorem which tells us that if you have a quantum field theory and it's invariant under the restricted component of the Lorentz group, that is, it's invariant under the bit of the Lorentz group that just includes boosted rotations but not any space or time reflections, then it will automatically follow that in addition, that quantum field theory is invariant under CPT, where CPT is the composition of charge conjugation, turn all particles into their antiparticles, parity reversal, change left hands into right hands, and time reversal, flip the direction of time, although it needn't be invariant under any of those three operations separately. So this theorem was first discovered in the early 1950s in the context of so-called Lagrangian quantum field theory, that is, the version of quantum field theory that one finds in the physics literature. Later on, when people developed more rigorous axiomatic approaches, Streeter and Whiteman style quantum field theory, algebraic quantum field theory, it proved possible to come up with highly technical, rigorous proofs of similar looking theorems in those approaches. And what you'll find if you look at physics textbooks now, and you look up CPT in the index and you see what they say about it, is the following rather frustrating situation. There'll be an extremely brief, hand-waving sketch of an argument of how one might go about demonstrating CPT in the context of Lagrangian quantum field theory. And then there'll be a little footnote which says, well, if you really want to know how the argument goes and you're rigorous-minded, look at Streeter and Whiteman. This state of affairs strikes me as unsatisfactory because, as I believe will be discussed in more detail tomorrow, in the first instance, the relationship between physicist Lagrangian quantum field theory on the one hand and Streeter and Whiteman et al. On the other is a little bit opaque, to say the least. You can't see what a Lagrangian would correspond to in the Streeter and Whiteman style framework. And secondly, while well-educated people are able to pick up Streeter and Whiteman's book, read the axioms, work through all the steps of the proof of quantum field of the CPT theorem, and see that the conclusion does indeed follow from the premises, the proof is sort of so long and convoluted and intricate that you're usually left with the feeling that you still don't know why the damn thing is true. And that's a bit frustrating. So it would be nice to come up with a much simpler argument, a more elegant argument, that would, in addition to convincing us that CPT is true, give us some insight as to why it holds. The bit about a fable about Feynman is the following. I don't know whether this is true or not, but I once read somewhere that sometime in the early 60s or maybe the 70s, Feynman was asked to give an evening talk to second-year undergraduates at Caltech, explaining, not the full techie details, but just the basic idea of the CPT theorem, what's really going on. And Feynman said, yeah, sure, I'll have a go at that. And he commented that this must be possible because, after all, if one can't explain something to intelligent second-year undergraduates at Caltech, the only possible reason could be that one doesn't understand it oneself. And then the story is Feynman spends a couple of months trying to prepare this talk, and then throws his hands and cancels at the moment. What I'm trying to do is better that, do what Feynman So the research strategy is one of asking stupid questions, as many as possible, and then trying to answer them Here are my 3 stupid questions. Stupid question number 1. The CPT theorem, gee, that seems like a queer sort of thing. Let's think about the symmetries involved there. The premise was about Lorentzian invariance, that's a spacetime symmetry. The conclusion involved 3 symmetries, parity and time reversal, those are also spacetime operations. And then there's this other thing, charge conjugation. So you might think, well, I can begin to see maybe how there could be a theorem proving some intimate connection between Lorentzian invariance and parity and time reversal, but I don't understand how there could be such an intimate connection between spacetime symmetries on the one hand and this non-spatial temporal thing on the other. So how can there be a CPT theorem in particular? Second stupid puzzle. Well, never mind that. Suppose that instead of a CPT theorem, we just had a PT theorem. So this would be a theorem which says that any quantum field theory that's Lorentzian invariant is also invariant under total spacetime reflection, x goes to minus x. Even that seems a little bit odd, because we normally think we're free to write down a theory with any symmetry group we like. In particular, we might think we ought to be free to write down a theory whose symmetry group was precisely the restrictive Lorentz group, the bit that just includes the rotations of boosts and no reflections. But yet even a PT theorem would be telling us that we can't do that. Anytime we try and write down a theory that's the Lorentz invariant, we're automatically going to get this larger symmetry group including reflections as well. Why is that the case? Second question. And then the third question is the following. It's normally thought that the CPT theorem is specifically a quantum field theoretic event. But when you do go through this exercise of going through the steps of the proof of the CPT theorem, it's not entirely clear why that should be the case, where specifically quantum features of the theory are playing a role. So this raises the question of whether it might be possible to prove the same sort of thing in the case of a classical Lorentz invariant field theory. If we could do that, then the answer to this question would be nothing at all, and that's what I'm going to do. Right, so briefly, what are we going to say about the other puzzles? The first puzzle, I think, just dissolves when we think a little bit more carefully about what's going on, as I'll explain in slightly more detail in a minute. I think it is more accurate to think of a theorem that's normally called the CPT theorem as just being a PT theorem. I think the transformation that's normally called CPT, in a certain sense, really just is PT. More to follow in a second. As for the second question, this is the one that's directly addressed in the paper that I posted on the conference webpage. Well, there are 2 ways you can tackle a question like this. The first is a sort of hard-headed way which says, well, if you want to know how it can possibly be that one symmetry entails another, work through the proof and you'll see how it goes. So in some sense I'm tackling this question in this talk as well. What that paper was doing was trying to tell a more high-level explanatory story about what's going on. And then finally, as I said, what I'm going to do today is try and sketch out a classical PT theorem. And insofar as that's successful, the conclusion is going to be somewhat mixed. I can almost get there, but I'm not quite satisfied with how far I can get in this direction. Insofar as it can be done, the answer is there's nothing specifically quantum about the CPT theorem. It really just follows from features of the Lorentz group, and it applies in the classical context as well. Okay, so this first point leads to a certain amount of confusion. So before I start talking about PT theorems without further ado, I want to say a little bit about why you should be satisfied with this apparent change of subject from CPT theorems to PT theorems. Okay, so what's going on here? I think the issue essentially boils down to semantics. What we do when we're proving a CPT theorem is we write down a certain set of transformations on a set of fields mathematically specified, and then we give names to those transformations like charge conjugation, time reversal, parity reversal, and we try to give arguments for why those names are appropriate, but those arguments are never absolutely watertight. There are always alternative naming conventions available which in different contexts might be more reasonable. So let me say a little bit more about this. Suppose I have, say, classical Klein-Gordon field theory for a single scalar field. So I have my Klein-Gordon equation, and I notice that if I have phi of the form e to the I ka xa, where this is the spacetime field vector, then this is going to be a solution of the Klein-Gordon equation anytime the square of k in a sense of a Gaussian spacetime square is the mass square. So any such phi with k satisfying this restriction is a solution of the equation, and similarly for any linear superposition of these. So I can draw a little momentum space diagram of these solutions. And I have my two mass shells. Two because the requirement that k squares to m squared doesn't tell me whether k is future or past directed. So I have this positive mass shell of future directed k's and my negative mass shell of past directed k's. And then if I'm going to build a quantum field theory from this, and if I want to talk about particles in my quantum field theory, what I'm going to end up doing is constructing a one particle Hilbert space from the space of positive frequency solutions, and I'm going to end up constructing a one antiparticle Hilbert space from the space of negative frequency solutions. So this be complex. The point here is the following. Suppose I consider a transformation which sends this state to that one. What should I call such a transformation? Well, if I'm thinking from the point of view of the phenomenology of particle physics, it's very salient that what I've done is turned a particle into an antiparticle. And you might think, from the perspective of particle physics, well look, what I mean by a time reversal operation, or a PT reversal operation, is an operation which takes a particle moving in a certain way to the same sort of particle moving in a different sort of way. So then, in that case, this won't count as just a PT operation because it doesn't give me back the same sort of particle, it gives me back its antiparticle. So I'll call that CPT. That was all from the perspective of particle physics. If, on the other hand, I'm more interested in the perspective of classical field theory, then it seems much more appropriate to call this a PT transformation because, after all I did was send k to minus k, and that's the sort of thing that PT does for four vectors. So my point is just, from the perspective of the mathematics of the CPT theorem, it's more relevant to think from the point of view of classical field theory than it is to think from the point of view of particle physics. And in that case, the thing that deserves to be called the time reversal operation in field theory is the composition of particle physics T and particle physics C, and so correspondingly, the thing that particle physicists call a CPT theorem, as a field theorist, I'm going to call a PT theorem. But it really is just semantic. Okay, so PT theorem tensor. My project, as I said, is to try and prove a PT theorem for a classical field theory. So I don't have a Hilbert space inside, and I don't have any operators under the Hilbert space. There are a few reasons why I think it would be nice if we had such a thing. The first is that, in contrast to the Streeter-Whiteman style stuff, I'm going to be able to write down Lagrangians in my classical field theory. So I'm going to be doing something which looks much more like physicist QFT than Streeter and Whiteman's group. On the other hand, since I don't have any operators, I don't have any problems with loss of mathematical rigor when I start multiplying operators at points and so forth. So I can really prove a theorem that's going to be absolutely mathematically rigorous. It's nice because it shows which features of the proof of the CPT theorem, it shows which features of quantum field theory are required for the proof of the CPT theorem, and which features, like Hilbert spaces and so forth, happen to be around for other reasons when we're talking about QFT, but really have nothing to do with CPT. And it's always nice to understand which assumptions are really required for our theorems and which are extraneous. And then finally, the reason I think this is going to be nice is that, as I said, one has, with the ordinary, or the known proofs of the CPT theorem, something of a feeling of black magic. You can follow all through all the steps, but you don't really get any insight. The things that we can prove in classical field theory and claim are not going to have this feature. They're going to be much more simple, much more elegant. You start to see why the PT theorem is true in the classical case. Okay, so here's an outline of the rest of the talk. The top bit, CPT theorem and reasons to be dissatisfied with the existing quantum field theory proofs, are the bits that I've already talked about. What I'm going to do next is split classical field theories into classical field theories for tensor fields first, and then I'll move on to talk about classical field theories for classical spinors. In each of these cases, we can prove a PT theorem, although the picture I'm going to paint is going to be somewhat more rosy in the first case than the second. in this section a minor cloud, I'm going to say why the picture isn't very rosy in the case of spinors, and then finally summarise where I've got to so far. So this bit in particular is the bit where I'm hoping that the audience is going to speak up and solve my problem. Okay. So let me start by teaching most of the audience to suck eggs. I'm doing this mostly because once we get onto spinors, it's going to be useful to have a familiar template against which to compare things. So we're starting by talking about tensor fields. I have a Minkowski spacetime, there's a manifold M, and there's a metric eta defined on M, which is flat and has signature 1, 3. We have a notion of a vector at any point in this manifold. This is an element of a tangent space. If we want, we can think of it as an equivalence class of curves, or whatever your favourite notion of differential geometry is. Once we've got the space of vectors at a given point, then we're away. We can define lots of other things and get tensors of arbitrary rank. We have covectors. These are linear maps from the space of vectors to the reals. And then we further have tensors of arbitrary rank R, S, where a tensor of rank Rs at P is a multilinear map from R copies of the cotangent space and S copies of the tangent space to the reals. In fact, we're going to be interested in tensor fields rather than tensors on their own for the purposes of field theory, where a tensor field beginning rank is just a smooth map from the space-time to the set of tensors of the appropriate rank over that point of space-time. This, for the purpose of proofs of the CPT theorem, is not going to be so important, so I'm sometimes going to talk about tensors and tensor fields interchangeably. Okay, so, alright, that was all very abstract. What about physical examples? Well, we have this sort of field in play in, say, electromagnetism. So here you have the Maxwell-Faraday tensor, that should be a 2. This has 2 lower indices, so it's a tensor field of rank 0, 2. And you also have a charge current density J, that's a 4 vector, it has 1 upper index, so it's a tensor of type 1, 0. And then once you've got a number of such tensor fields in play, you can write down differential equations that couple them. And this is what happens in Maxwell theory. You have these equations, which one can think of either in coordinate independent form as relating, in this case for example, 2 4 vectors to one another, or you can think of them equally well in coordinate dependent form, in which case this would be a set of 4 equations relating real value quantities. Okay. Second account of what a tensor is. So the point here is when I get onto spinors, I'm not going to do anything analogous to that construction from tangent spaces that I gave you when I was telling you what a tensor is. That's because I don't need to. The only features of tensors that we need for the purposes of PT theorems are the dimensionality of the vector space they live in and the way in which the Lorentz group acts on them. So I want to strip away the rest of the stuff and just retain that. Okay, so we have the Lorentz group. The Lorentz group is isomorphic as a Lie group to the following matrix group. You have this 4x4 matrix representing the metric, which is diagonal, has 1 minus and 3 pluses, or the other way around, depending on which sign you've chosen. And then a 4x4, okay, this could be real or complex, depending on whether we're talking about the real or the complex Lorentz group. This Lorentz group is the set of 4x4 matrices that leave the metric invariant in this sense. And then you have a natural action of the Lorentz group on the space of tensors of any given rank. So what the Lorentz transformation fundamentally is doing is moving the spacetime around, so mapping spacetime onto itself. So if, for example, you were thinking of say, vectors as equivalence classes of curves, well, all the curves in the equivalence class will be being moved around. So you're taking one vector to another. And since we've built tensors of arbitrary rank, by starting with vectors and talking about maps of vectors and reals and to the reals and so forth, what this is going to do is induce a map from the space of tensors of any given rank to itself. And when we work through the details, the way it turns out is that if you have a tensor of type R, S that has R upper indices and S lower indices, and you act on that with a given Lorentz transform L, the result is just this long multiplication which is missing a T at the end. But you've got R plus S copies of the matrix L multiplying the original tensor, and that's our transformation law of tensors of this type. So the point is we can now take away the ladder that we started with. We can throw away the construction from curves on the manifold and so forth, and just take the space of tensors that we're given back to be a vector space of the appropriate dimension, equipped with this action for the Lorentz group. That's all we're going to need. Okay. So that's what a tensor is for our purposes. Now we want to talk about PT theorem. So we want to go back to this notion of differential equations for our tensors and ask about the symmetry groups of various sets of equations. So, as we said, for any given tensor field, we know how that tensor transforms under an arbitrary Lorentz transformation. So we can start asking questions like the following. Go back to Maxwell's equations. Is it the case that any time f comma j is a solution of the equations, the quantities that you get if you transform that f and that j by a given Lorentz transformation is also a solution of Maxwell's equations? In other words, are Maxwell's equations Lorentz invariant? When here I mean restricted Lorentz invariant, that is, we're not allowing any reflections yet. And of course the answer is yes. You can further ask for the same set of equations. Okay, now let's consider transformations that do involve reflections. Is it the case that any time f comma j is a solution of Maxwell's equations, the quantities that you get if you transform f and j by total reflection, x goes to minus x, are those going to be quantities that solve the total reflective Maxwell equation? What I mean by total reflective Maxwell equation is you need to send du to minus du as well, as it would if you were thinking of this static coordinate transformation. And you only have to stare at those equations for a couple of seconds to see that the answer to that question is yes as well. So what we have here is a situation where we wrote down Maxwell's equations for a couple of simple tensor fields, and the following material conditional was true in this particular case. If the equations are restricted to Lorentz invariant, then they're also PT invariant. But that was just one particular case, and what we're after is a general theorem. So what we want to ask is, well, was that just a coincidental feature of Maxwell's equations, or is it that something that's going to turn out to be true in general for classical, for theories of classical tensor fields in general? So here's a conjecture. It's a somewhat underspecified conjecture, so we've got these parameters split in there. Is it the case that any time I have a system of dynamical equations satisfying some set of restrictions yet to be spelled out for a collection of tensor fields, that is, objects that transform in the right way under Lorentz transformation, then if those equations are restricted to Lorentz invariant, then they're also PT invariant. And my claim is yes, for suitable specification of the restrictions, and not very worryingly restricted ones, this can be done. And this statement is the classical counterpart of the CPT theorem for dynamical systems of classical tensor fields. So it's a special case of a more general type of thing, and in general invariance theorem will be a statement of the following form. You've got some solution set S to some family of equations satisfying some restrictions R, for mathematical objects of type X. You've got some group G, and you've got defined an action of G on the space of kinematically allowed fields of this theory. You've got some subgroup G prime of G. You're supposing that the equations are invariant under G prime, and you want to know whether it follows from that the equations are invariant under the whole of G. So this is the abstract form of what we're doing, where in our case the restrictions are the ones that I haven't yet told you, but I will in a minute. The mathematical objects of type X are tensor fields, or things that transform like tensors under Lorentz transformations. G prime is the restricted Lorentz group, and G is the larger Lorentz group, including the total reflection component as well as the no reflections component. Alright. Okay, so I said at the start that I was going to throw more maths at you than I myself will be happy having thrown at me. So what I want to do next is just very briefly sketch how the argument for that claim goes. But you have my full permission to glaze over at this point if you wish, and I'll tell you when to wake up again. But for those who do want to know how it goes, here's the deal. It's just an analytic continuation argument. So, going right back to what I guess they teach in maths undergraduate year 1, although I never did that myself. When you do complex analysis, you learn the following sort of thing. Suppose you've got a function on the complex plane. So it's a function from the complex numbers to the complex numbers. Suppose you know that it's everywhere complex differentiable. Suppose you know its values on a real line. Then you've got enough information to work out what the function is doing on the whole of the complex numbers. This is the sense in which the requirement of complex differentiability is much stronger than the requirement of real differentiability. So this fact enables us to prove little lemmas of the following sort of form. Suppose I've got such a function, and suppose in particular that it's polynomial in its argument. That is, we can expand it in the following form: f of z equals sum from I to p, some integer p, complex coefficient times complex variable. And suppose if this expression correctly gives the value of f everywhere on the complex plane. Suppose further that f vanishes on the reals. Well, then we can see that f is going to vanish on the whole of the complex numbers. We can see that very easily in this case, because the only way it can vanish on the reals is for all these coefficients to vanish, and in that case, of course, it vanishes everywhere on the complex plane. Okay, so what we've got is an argument which allows us to conclude from the fact that some function vanishes on a subset of its domain that it vanishes everywhere. What's going on in the classical PT theorem is not different in kind from this. We've just got a few more variables floating around. Okay, so we prove the theorem in two parts. In the first part, we just prove a lemma about functions of the Lorentz group that's precisely analogous to that little lemma about functions of the complex plane that I flashed up a minute ago. And then in the second part, we apply this to get our PT theorem. So the lemma about functions of the Lorentz group is like this. Suppose I've got a function from the Lorentz group to the complex numbers, which is polynomial in the matrix entries of its argument. So any such argument is a 4x4 matrix. I've got 16 numbers there. I can consider functions that are polynomial in that set of 16 variables. Suppose this function vanishes on the bit of the Lorentz group that doesn't include any reflections. Then it follows by a similar sort of analytic continuation argument that the function vanishes also on the total reflection component of the Lorentz group. And if you like, the reason for this is that when you complexify the Lorentz group, these two components get connected to one another. These are the two bits that have determined 1 as opposed to -1. And then it's an extremely short step to get the result that we want. Okay. So here's how it goes. Suppose I've got a theory like Maxwell's theory, or something more general of the same kind of form, whose dynamical equations take the form of differential equations for a number of tensor fields. In that case, I can express each such equation by writing down some functional of the classical tensor field configurations and saying that that function evaluates to 0 on dynamically allowed configurations. Once I've got any such function f, what I can do is I can choose a particular set of field configurations. And the cases we're going to be interested in are the cases where I pick a set of field configurations that satisfy the equations of motion. And I define a function h indexed to that particular set of field configurations on the Lorentz group. The way I do it is I say, well, for arbitrary Lorentz transformation L, h indexed to these fields evaluated as L is just defined to be equal to my original functional f evaluated at the Lorentz transform fields. So the point of doing this is that it's given us translation from our original dynamical equations to functions on the Lorentz group. That is, the kind of things with which the lemma that I just talked about deals. Okay. Now we need some translation schemas. These are also very straightforward. What it amounts to in this language to say that the equations are invariant under the restricted component of the Lorentz group is just the following. If you started by picking field configurations that satisfy the equations of motion, then anytime you're plugging in, well, okay, then in the first instance, f of those fields will vanish. But then if the equation to Lorentz invariant is also going to be true, then anytime you plug in a restricted Lorentz transformation, f of the transformed field is also going to vanish. That is, this function h is going to vanish on the restricted component of the Lorentz group. Translation of the statement that the equations are PT invariant, on the other hand, is the statement that the same function h vanishes on the PT component of the Lorentz group. So now you can see why this is useful. We already had a statement that any function that vanishes on the restricted Lorentz group is going to vanish on the PT component of the Lorentz group, provided only it's polynomial in the matrix entries. If we impose the restriction R that the dynamical equations are polynomial in the tensor fields, then it is going to follow that this function H is polynomial in the matrix entries of L, and hence we have a PT field.
You mean in then finitely their derivatives as well? In their derivatives.
Okay, right. So here's what I'm doing with derivatives. Anytime I have a tensor field, if I take its space-time derivative or its double space-time derivative or anything like that, that is also going to be a quantity which transforms like a tensor of a given rank, albeit a different rank from the original one. So I want to just subsume that case under the original case. If my equations involve d mu of f as well as f, then d mu of f is one of these fields. Alright, so now is when you can wake up again and do this. What was the point of all of that? The point of all of that is that we've proved the following statement. Everything I've said, by the way, is essentially an elaboration of an argument that was given in a very nice 1955 paper by John S. Bell, which doesn't seem to be very well known. This is our classical PT theorem for systems of equations of tensor fields that are polynomial. If you have a set of solutions S to your dynamical equations, and your dynamical equations are polynomial, and if your set of solutions is invariant under the restricted Lorentz group, then it's also invariant under all proper Lorentz transformations. By proper, I mean determinant 1, i.e. I'm including PT. So we've got this statement: if your equations were Lorentz invariant and they're also PT invariant, that's exactly the same sort of thing that we were saying in the case of quantum field theory, but we didn't need anything constant. And this is nice, because although I said you could glaze over if you wanted, it wouldn't have taken you more than 5 minutes to work through what I said and see that all that's going on in a simple little analytic continuation like this. So the mathematics is very simple. We can see why we get a PT theorem. It's just because of this fact about the Lorentz group that PT gets connected to the identity when you complexify. By the way, we can now see why we don't have a CPT theorem for Galilean quantum field theory. That's because the analogous statement about the Galilean group is not true. It doesn't use many features of the theory. We just needed to know that our dynamical equations were polynomial and that our fields were transforming like tensors. And it applies to a more general class of theories, because we've isolated which features we were really using and chucked away the experiments. So as far as tensors go, I'm pretty happy with all of that. And there doesn't seem to be anything essentially quantum theoretic about the CPT theorem. However, when you look at an arbitrary Lagrangian on an arbitrary page of an arbitrary QFT textbook, you'll be very lucky if you find something like 5 to the 4 theory that doesn't involve any fermions. In general, we want to be able to deal with cases where we've got spinors floating around as well as tensors. So what I want to try and do next, and this is where the degree of success is going to take a bit of a nosedive, is do the same sort of thing for classical field theories, for classical spinor fields. So in time, I hope. Alright. So let me just give a bit of a sketchy overview of this. What's going on is extremely similar, very similar in kind to what went on in the tensorial units. All I'm going to change is the group that I'm working with and the transformation of. So whereas we previously had the Lorentz group, for the case of spinors I'm going to be talking about the covering group of the Lorentz group. And whereas we previously had tensors of various ranks, I'm going to replace that tool with the rank spinors. Okay, so here are some facts. If you consider the restricted Lorentz group, that group has an intimate relationship to the group SL2C, that is, the group of 2x2 complex matrices that have determinant 1. The relationship is that that thing is the universal covering group of the formal thing. And the reason that's interesting is if you're interested in representations up to phase of the Lorentz group, then you want to look at true representations of its covering group. Okay. I want to talk about PT as well as restricted Lorentz transformations. So I don't want to look at the universal cover just of the Lorentz group. I want to look at the universal cover rather of the proper, that is the determinant 1 component of the complex Lorentz group. And it turns out that the covering group of that thing is 2 copies of SL2C. So if if I want to find something in the universal covering group of the connected component of the complex Lorentz group, I need two 2x2 matrices, A and B, where each of A and B live in this thing. We need a couple of facts about this covering map. So if I just give you two 2x2 complex matrices A and B, and I ask you to project that down to the Lorentz group using the covering map, what do you get? What we need to know about the answer to that question is the following thing. If B was equal to A, if I gave you two copies of the same matrix, that's going to project down to a real restricted Lorentz transformation, that is one that doesn't involve any reflections. If, on the other hand, I gave you B equals minus A, then that's going to project down to a Lorentz transformation that flips both time sets and parity, but it's still a real Lorentz transformation. So then in place of tensor fields, we're going to think of Dirac spinors. A Dirac spinor lives in a 4-complex dimensional vector space, and in place of the transformation law, which told us how Lorentz transformations act on tensors, we have this transformation law telling us how elements of SL2C plus SL2C, that is, things like this, act on Dirac spinors. An important thing here is this complex conjugation. I'll come back to that in a bit. Okay, the point about talking about Dirac spinorial tensors is that I also want to be able to deal with cases of higher spin, and that's what this is supposed to do. Okay, so then similarly, just as we started writing down differential equations for tensor fields, we can write down differential equations for spinor fields, that is, objects that assign in a smooth way a Dirac spinor to each point of space-time. An example of this being the Dirac equation, where we think of this as a classical spinor field rather than as a line function. Now, when one starts talking about classical spinor field theories, one sometimes meets a certain amount of resistance. So I want to tell you why I think it's okay to talk about such theories. The first objection that's sometimes raised is, look, spinors are supposed to anti-commute. That makes sense in the quantum context because they're operators, so we understand what anti-commutation would amount to. But it doesn't make sense in the classical context where they're just numbers. The reply to that is, well, if you want them to anti-commute without being operators, we know how to do that. It's called make them Grassmann numbers rather than ordinary complex numbers. So there's no mathematical obstacles to making them anti-commute if we want to. In fact, I'm not going to. This is somewhat interesting because CPT is normally taken to require spin statistics, and I think there's a sense in which it does, but I haven't yet got to the point where I need it. Okay, second possible objection. Spinors are going to pick up a sine flip under a 2π rotation. That's okay quantum mechanically because we don't think that global phase factors are physical anyway, but it wouldn't make any sense classically. Okay, I don't think that this is a good objection to talking about classical spinor fields either. Let me skip over this in the interest of time. We can come back to it if you want it. In any case, the reason I'm talking about them is just this. I'm not thinking that I can really go out in the world and find classical phenomena that are well modelled by classical spinor field theories. That's not the point of the exercise. The point of the exercise, as I said at the outset, is just I'm trying to understand better the mathematics of the CPT theorem, and by considering invariance theorems for such classical spinor field theories as these, I think we're going to be able to get some insight into what's going on. Okay, so then what we want to try and do is prove an invariance theorem for spinors, analogous to the one that we were able to prove for tensors. So recall, if you went to sleep at the time, that proof had 2 steps. The first step was prove a lemma about functions of the relevant group. In the tensorial case, the relevant group was the Lorentz group. Now it's going to be SL2C cross SL2C, the covering group that I was talking about a second ago. And then the second step was just how to translate that into the invariance theorem by replacing curly f with these functions h of the relevant group. So we've done that for tensors, we want to know whether we can do it for spinors. And the answer is yes. We have to be careful about how we do it. This is important and annoying, and it's the reason why I'm not as happy with what's going on in the spinor case as I am with the tensor case. Okay, so what we proved in the tensor case, recall, is that if your function was polynomial in the matrix entries of L and vanished on the restricted component, then it vanished on the PT. So by analogy with that, you might think that what we're going to try and prove in the spinor case is, well, if a function of SL2C equals SL2C is polynomial in the matrix entries of A and B, and if it vanishes on those elements of SL2C equals SL2C that map to restricted Lorentz transformations, that is, cases where B equals A, then it also vanishes on the whole of the group. So in particular, it's going to vanish when B equals minus A and the mapping to a total reflection of Lorentz transformation. Well, wish for that if you want, but I wouldn't bother because it's obviously false. If you let F be, for example, this polynomial, that's going to vanish any time B equals A, but it's equally obviously not going to vanish in general, and B can be whatever it likes. But when we think about it a little bit more closely, fortunately, this isn't the statement that we want anyway, and the reason it isn't the statement that we want is this feature I highlighted a second ago about how Dirac spinors transform under SL2C plus SL2C. We have A here, but we have the complex conjugate of B there. And what that translates down to, when we work through the maths of the theorem, is that we don't want to be considering functions that are polynomial in A and B. We want to be considering functions that are polynomial in A and the complex conjugates of B. And we want to be able to argue that if you've got a function like that, and it vanishes whenever B equals A, then it vanishes everywhere. And this is true, and we can prove it by an analytic continuation argument just as simple as the one that we use. Well, I didn't show you it, but just as simple as the one that was in the background in the tensor case. And then, in precisely the same way that we translated our lemma about functions of the Lorentz group into a classical PT theorem for systems of tensor fields, we can translate this lemma about functions of SL2C plus SL2C into a PT theorem for classical spinorial field theories. The restrictions are the following. We have to assume that our dynamical equations are polynomial in the spinors. It turns out to follow from that that these functions H we were talking about are polynomial in the matrix entries of A and B bar. The reason being that when you write down the expression for this according to the given transformation law for Dirac spinors, you don't get elements of B multiplying elements of psi, you get elements of B bar multiplying elements of psi. It turns out to follow from that that if F was polynomial in the spinors, this thing is polynomial in the entries of A and B bar, and so we can apply our theorem. Okay, so upshot of that bit, we have the following classical PT theorem for polynomial systems of spinor fields. If you've got a collection of partial differential equations for spinors, and if they're polynomial in the spinor fields, then if your equations are invariant under the bit of the coupling group that maps to the restricted Lorentz group, they're also invariant under the bit of the coupling group that maps to PT. In this sense, we have a PT theorem for spinors, and to note that, I haven't appealed to spin statistics. I don't know whether that's a good or a bad thing, but I haven't. Okay, so why am I not jumping up and down with joy? The reason is that I think in the case of spinors, although I also think, not in the case of tensors, this isn't as general as we want. And the point is, spinors are complex. And when you look at the grandians including spinors, they tend not to be polynomial in psi. They tend to have these annoying psi bars floating around. So we seem to be interested in cases where we've got dynamical equations that are not polynomial in psi, and quantum theoretically at least, we seem to have a theorem, PT, CPT, whatever, that covers those cases as well. So it looks as though I have failed to capture in the classical case the full generality of the quantum field theoretic CPT theorem, and that's bad. We could do better if, counterfactually, we had a lemma about functions of the covering group that said, well, anytime your function is polynomial in the matrix entries of all of these guys, originals and complex conjugates, then if it vanishes on the bit that projects to the restricted Lorentz transformations, it also vanishes on PT. But the little example I wrote down earlier, F is the first row, first column component of A minus the first row, first column component of B, shows that that's false. That function is polynomial in these things. So, what to do? Okay, here's where I'm really unsure. Here's a thought which I tried for a while, but I don't think works. Normally, in the quantum field theory literature, that is in the Lagrangian context, one is interested in proving statements about invariances of Lagrangians. We're normally trying to argue that if our Lagrangian is Lorentz invariant, then it's also CPT invariant. So far, I've been talking not about Lagrangians, but about systems of equations of motion. That is, don't look directly at the Lagrangian, look at the Euler-Lagrange equations you might derive from that Lagrangian. And then you think, well, okay, I could have a Lagrangian which contains a term of the form psi bar psi, but still when I was getting the Lagrange equations from that, I would be functionally differentiating with respect to psi bar to get equations for psi. And so even though the Lagrangian isn't, the Euler-Lagrange equations would be polynomial in psi. That's a line of thought you might try. So to get this to work, you would need an argument to the effect that Lagrangians can never have more than one psi bar floating around. Because obviously if I had a term like this, psi bar psi, and I differentiate that with respect to psi bar, I'm not going to get rid of both of these psi bars, I'm only going to get rid of one of them. And so I'm not going to get either the Lagrange equation for the polynomial in psi alone. And so I still don't have the theorem that I want. So you might try to argue that Lagrangian terms like that can't appear, and I played around with a couple of ways of trying to outlog them, neither of which I think work. The first way was to observe that terms like that aren't renormalizable. When you carry out this sort of count the mass dimensions game, I think the Dirac spinner has mass dimension 3 halves, right? So something like that would have mass dimension 6, and that's too large, so it won't be renormalizable. So you might try to rule out Lagrangian terms like this on background. But even if you could, I don't think that would be satisfactory, because CPT is surely a much more fundamental result than any considerations of renormalizability. So I don't want to prove from the CPT theorem to depend essentially on appeals to renormalizability. The second thing we might try is making our spinors anti-commute, which, as I highlighted, I haven't yet done. In that case, you can say, well, there's no point writing down terms like this, because they're going to vanish anyway. You can always anti-commute psi past the psi bar, pick up a sign flip in the process, and now you've got psi squared, which will vanish my anti-commutativity. Okay for the term I originally wrote down, but the reason I don't like this is if I had kinematically independent spinor fields, then this trick won't work, because although psi squared is 0, there's no reason why psi 2 psi 4 has to vanish if those are two different spinor fields. So I don't know how to get rid of the Lagrangian terms that violate my polynomiality restriction, and so I don't know how to prove a PT theorem of sufficient generality for spinor fields. The alternative strategy one might pursue is to go back to the drawing board, chuck out this analytic continuation argument approach that I've been appealing, look directly at the invariances of Lagrangians, impose anti-commutativity the way everybody else does, and then start talking about processes of complex conjugating Lagrangians, insisting that the Lagrangian be real, commuting operators past one another, counting the sign flips and so forth. And you can do all of this, and you do get a PT theorem, but the problem is, while there's a nice feature of this, which is that we've still shown which features of the quantum theory weren't required, we still didn't need any operators or Hilbert spaces, we haven't anymore got a simple, elegant argument that illuminates what's going on. We're playing around with precisely the same sort of black magic that I was accusing the original quantum field theory literature of doing. So I can give this sort of argument, but I don't like it. Okay, so here's the summary. I started out with a sense of dissatisfaction at the fact that existing sketches of proofs of the CPT theorem in the Lagrangian QFT literature are very ugly, and so don't really explain why CPT is true, although we might convince you that it's true. When we were just focusing on tensors, it seems that we can do a lot better, and in fact that Bell has done a lot better. We've got a very simple proof. We can see why the PT result just follows from elementary features of the Lorentz group, and that's very nice. The problem is that we also want a PT theorem for spinors, and in this case it doesn't seem to work out. We can give a proof surprisingly not involving appeals to spin statistics for systems of equations that are not known as spinors, but that doesn't seem to exhaust the class of cases that we're interested in. Okay, thanks for your attention.
Can you get back to the bit where you had actually what we're trying to prove with the spinorial case is something a bit stronger than CPT. And it seems to me that you're trying to prove that if theory is invariant under the restriction I exclude, it's invariant under classification. Now, I take it all we actually need is that it's invariant under the real.
That's right. Yeah, so the only reason for doing that is when I look at the sorts of proof that I can give from this continuation, either in the tensor case or in the spanner case, that extra strength comes from.
So it'd be an interesting question to ask if I can in context.
So I'm betting the answer is no, but
Yeah, I'm going to waste your precious time with a non-technical question. So in quantum field theory, if I take a system that has a charged field in it, and I act on it with what you call the PT operation, I don't reverse its charge, whereas if I take a system like that and I act on it with what Joe physicists would call the PT operation, it does reverse its charge. So that's the difference in nomenclature between you and, right?
isn't it the other way around?
Is it the other way
My
around?
PT operation is what everyone else calls CPT.
Oh, right, right. Wait, oh yeah, okay, good, yes. So what happens if you do that to something like a classical Yukawa system, or to, classical Maxwell theory if it's interacting with a charged field? I mean, if you perform your PT on it, will it reverse the charge of the charged field, or will it leave it the same?
I think this is the issue that we were discussing on the way over here this morning about what you think about the so-called fine viewing classical electromagnetism. So the analogue of what I'm saying about PT here would be what Frank and I call the fine viewing classical electromagnetism. So there you have PT flip over the charge current density.
Yeah.
And the way we were suggesting thinking about that is, well, it hasn't changed the charge, but it has given you a path-directed form velocity. Then there's this other point of view which says, come on, that doesn't make any sense. Form velocities were always future-directed, so you must have flipped the sign of the charge.
I mean, one question about having path-directed form velocities is, presumably you're going to have path-directed energy momentum vectors. So how are you going to have a theory with a mass gap, right? When you can have, a theory with, a highly negative momentum 4 vector. You have a state with a highly negative momentum 4 vector and one with a highly positive one. It's just a little bit more, and you sort of add them together, right? You get a state with a teeny little bit of energy, and then so the minimum energy looks smaller than you would expect. It's kind of like the question, why don't we fall off into the infinite drop if our Hamiltonians aren't bounded below?
Right. So I don't know in detail how the answer to that question works out, but I mean whether or not we keep on cascading down if our energy is bounded below depend on Hamiltonian. And since all we're really doing is a relabeling trick, I find it impossible to believe that what we're saying doesn't turn out to be empirically equivalent to the usual story.
I had that feeling too, yeah.
I thought you said this was going to be a non-technical.
Oh, well, sorry.
But I don't know how to say more than, come on, it must be empirically equivalent.
Yeah.
So I think you said all you're going to say about statistics, or did you have more to say about why you think that doesn't come in, or whether you're worried that it doesn't, or?
Well, I mean, I'm worried that it doesn't in the following sense. Everyone else says that spin statistics is required for CPT, so if I haven't yet found a role for it, there's likely something that I'm missing out on. But no, I don't have a great deal more to say about it.
Okay. Second thing, I think you're not going to like this approach. Have you tried, I don't know if this is possible, but looking at axiomatic presentations of such theories and then trying the Streeter-Whiteman way of getting at some analog of the Streeter-Whiteman way of getting the results?
I mean,
I
I did what I said. I read
right,
through Streeter and Whiteman's book and I said, oh yeah, axioms and comes out 60 pages later. But
Well, okay, but that's for the quantum case, right? But could you do?
oh, I see. You mean can I give
can you get
an
a
axiomatic
classical
classical field theory?
Yeah.
Right.
And
Okay.
then,
Okay.
like, I know that you wouldn't probably be happy with that answer, but at least you know there was one. That maybe you can give you some ideas.
I mean, maybe
about.
it's what I'm doing. I'm axiomatizing that my dynamical fields are tensor representations of the Lorentz group. And the
Right,
equations
yeah,
given by polynomials. I'm not sure what else an axiomatic
Right, and you're
classical
doing
field
this
theory would look like.
straightforward thing.
And it's a continuation.
Yeah. Okay.
So I guess my functions H are classical Whiteman
So
functions.
what you actually need then, I guess, is that you have the tensor case, you have the axiomatization you need, but you're still unclear, you know, good these terms, about how to axiomatize the spinor case. Is that true, or? I know you don't want to play those terms, but.
No, it's more that I know how to prove the theorem when I write down excessively restrictive axioms for the spinor case. And I don't when I write down axioms that cover all cases of polynomials.
So it's a perfect thing for the axiomatic approach.
Okay, so flash coordinate works.
Can you say more about the what goes wrong by Galilei?
Sure. What do I say? I mean, so
So
it's possible to write down classical field theories for tensors, say, which are invariant under Galilean boosts of rotations, but are not invariant under total spacetime.
and what stage in your if I try to copy you,
Yeah,
right? At what stage in my
right. You would
in
get
my group would things go wrong?
you would get stuck because the PT transformation is not connected to the identity and the complexification of the Galilean. So you wouldn't over time let it continue from one to the other.
So there's a sense in which I kept wondering whether we really needed the detour through complex analysis. It sort of seemed plausible when you first see it, like, oh, if these things are polynomial and they vanish on this big open set over here, they must vanish on the other one too, but you're telling me that's not. That way of thinking would get you into trouble with Galilei.
Yeah, so I can say something more about Galilean as well, which avoids this analytic continuation stuff, because I share the sense of, look, we're interested in real space-time, right?
Yeah.
So how can it be that everything we want to say about real space-time can only be said by these details into complex numbers? So in the paper that I posted on the conference archive, I was offering an alternative explanation of why you don't get a PT theorem for Galilean field theories. So in brief outline, the explanation I was offering there was something like this. Claim you would expect to get a PT theorem just in case you were able to find some tensor field which represented temporal orientation without breaking Lorentz invariance and Galilean invariance respectively, depending on which case we're interested in. In the Lorentz invariant case, you can't represent temporal orientation by a tensor field. So you can think of choosing a vector, then you've accidentally picked out a preferred time-like direction. You can think of choosing a one-form, you've accidentally picked a preferred time of simultaneity. And Lorentzianly, neither of those things are allowed. Galileanly, however, I am allowed to pick out a preferred standard of simultaneity, so I can write down a Galilean invariant one form, just write down some global time function and take its derivative. And then that's a bit of space-time structure that I can couple to other dynamical fields and then suppress into the background. And I'll have field theories that are Galilean but not PT invariant.
First, a question of clarification. Were you allowing yourself in the classical analysis to consider, for instance, complex tensor fields, as well as, I mean, when you dealt with Dirac equation, you had to have some components of the field complex or mathematics. But did you allow yourself complex fields for tensor fields?
Yeah, I did.
You did. Okay. Now, I wasn't objecting to that. I wasn't sure that you had, and I thought you should. So, because in the quantum mechanical case, we wouldn't even have a meaning for the charge conjugation operator unless we had non-Hermitian fields.
Right.
The other point that I wanted to make was sort of against the spirit of combining C and T into just a T. As natural as that assumption sounds, and I agree that it's natural, and that is we have the one empirical case of K-mesons, which not only displaying violation of parity conservation, as the whole weak interaction does, they violate PC. They don't violate PCT, of course, but they violate PC, and therefore they must violate T conservation. So that's one instance in nature where the C seems to go with the P rather than with the T.
Okay, but hang on. Why am I not allowed to re-describe that case by saying, okay, so sorry, you're saying that the K-mesons violate PC. So
Right.
Well,
I thought what you wanted to do was essentially absorb C into T and make that just one.
I mean, the situation's symmetrical, right? So my okay, so the bad guy is the particle physicist. He gets a subscript PP, and I get back T. So T mine is T is C is, but also T is T mine, C mine.
If
So,
C is C yours.
right.
Okay.
So, I mean, I don't really see why these K-mesons push me into
Okay,
using one of
the
my
theorem we have is TCP conservation, whether it's his or yours.
No. The theorem we have is his TCP and my TT.
Right. Yes. But what do the K-mesons look like with your PT? They violate P conservation, so they must violate T conservation, your T.
Yeah.
But they also violate CP conservation.
Which is also my CP, I suppose.
Yes.
Because my P is his P and my C is his C.
Oh. Okay. I don't see that
Okay,
yet. But
can I come back to your first
Yeah.
comment?
Yeah.
Okay, so I thought you were going to press me further on this. So I started worrying in the case of spinors that I couldn't just say, of course the equation is going to be polynomial because spinors were complex, so we might have complex conjugates that are floating around. So I thought you were going to say, well, if you're going to allow the tensors to be complex, then why can't you have the Lagrangians that contain terms like phi star, phi for tensor fields, and why am I not going to have the same problem there? So I think the answer to that is something
Good
like...
question.
That's right. So I think the answer to that is something like this. If you tell me I've got a complex tensor field, I'm free to disbelieve you and say that I've got two real tensor fields.
Well, that was the direction I would have gone. In other words, mistakenly thinking that you hadn't allowed yourself complex tensor fields. Then the next question would have been, if you had said yes, you hadn't allowed it. Is there any real difference like that? Can you get away with just thinking of just the sum of the two real parts, one of which has imaginary?
Yeah, so I think that I can in the case of tensors, but I'm worried that I can't in the case of spinors.
Yeah, right.
And the difference is that if I have a complex tensor field and I say no, it's really just phi 1 plus phi 2, where phi 1 and phi 2 are real, then I've got Lorentzian transformations acting on the whole thing. So by linearity, I'm just transforming each of L1 and L2 separately by Lorentz transformations, and those Lorentz transformations are real matrices. But if I'm talking about spinors, then the thing that I'm transforming my spinors by are complex, so I can't say I've only got real spinors and then use these matrices. And then I can go to them on one basis and things are different, but then I go.
So I've got Steve, David, and Hughes.
This is a quick question, maybe a question, but it's called to mind by David, maybe this is what you're getting at. I'm just wondering, you're trying to get back in the classical case, the result that streamer like you get from the quantum case in the algebra and the constructive in the context of like the axioms, right?
Yeah, or probably more accurately the result that Harry et al. Originally got in the random quantum field theory, but by this incredibly convoluted line.
Right. So, I mean, the main difference, and you're wondering what quantum theory would have to do with it, the only thing that strikes me, so this is just a question, is that quantum theory requires that there's a unique vacuum, the energy bounded from the. And I'm wondering where that comes into the streamer enlightenment. Because that's the thing that you don't get to avail yourself of. Is that something you thought about?
Too long ago, yeah, I don't remember what role that plays exactly in the speech format. I take your point there. That would be a place to look.
It kind of follows on Lorentzian's suggestion. All this thing here, the spinor field is not observed in classical property. What we observe are bilinear products of it, which transform tensorially.
Yeah.
And as I recall, the axiomatic framework is actually ultimately not in terms of these things. The spinors are sitting there circle structure, even within fields. Now, what I don't know offhand is whether, let me take an arbitrary spinor theory, write down a big wodge of tensorial constructions for it. Whether by specifying those tensors and sufficiently many of their derivatives on some surface, I effectively specify the spinors, would be clearly uniquely up to something I don't care about, say. In that case, then it seems to me your tensorial argument goes straight through for those constructions, and would tell you that all of the observable consequences of the spinorial theory were PCT invariant, PT invariant, PTs I believe.
Right. I mean, that sounds sort of like what goes on in the proofs that I don't like, where you say, well, first, if we're going to take the Lorentz invariant, it must be a similar product of Dirac bilinears, and so forth, and then how the Dirac bilinears transform. I suppose the hobby horse that I'm riding is the sense that there's more insight to be gained by looking directly at the nature of the group of the spinners themselves based on representations of, rather than this trick where you just look at their bilinears and think about their distribution and so forth. It's conjecture.
Sure. I mean, the thought is that if what you're after is an insight, and you know what's going on tensorially, so one possibility will get something directly to the audience, but an alternate route says something like, well, look what's going on at the level of what has physical salience, what's observed in operations active, but what's doing the physical donkey work is always tensorial, whether in a spin half or swinging case.
I'm not sure that you would say that everything that's doing the physical bit, the work is tensorial once you stop doing operations. I mean, there's a reason we don't just formulate that theory in terms of tensors in the first case, we start talking about spinners. Right? They're not just eliminable mathematical constructs. And I suppose the other answer is, yeah, maybe what I'm after is not best characterized as being physical inside of more mathematical inside.
I wanted to raise again with this group the issue that I raised at lunch. It's already come up. It really does concern the other paper or its relation to this one, but it did come up in your response to Gordon. If in the case of a theory posed against the background of custom space-time, our guide to why we should expect to have a CPT theorem or a PT theorem is the fact that we can't express temporal orientation in tensors, then the fact that we can express temporal orientation in terms of spinners might well lead us to believe that we shouldn't have a CPT or a PT theorem for fermionic fields. So given that, what is the relation between that intuition and the presentation today?
Right. So, as you know, I don't know the answer to this question. Yeah, so prima facie I would have expected that given that we can construct a Lorentz invariant temporal orientation for spinners, we should not get a PT theorem for spinners. And it seems to be the case that once you do allow psi bar in addition to psi, that's indeed the case, provided you're not having your spinners be anti-commuting objects. So if your spinners were just ordinary commuting variables, like complex numbers and commuting variables, then, fact, you don't get a PT theorem. Conjecture, it's going to be possible to explain why this is the case by appeal to this Lorentz invariant temporal orientation that one can construct using spinners. Am I yet in a position to substantiate that conjecture? No, but I hope that it can be done. And then the additional epicycle on this is, gee, isn't this a strange thing if I didn't have my spin as anti-commute, then I'd be able to violate PT using this temporal orientation, and then somehow once we do have the spin as anti-commute, we get the sign flipped in just the right places to eliminate the ability that we used to have to construct PT violating theories using temporal orientation. What's the relationship between anti-commutation and PT such that that's possible? Answer, I have absolutely no idea.
So this is back to the second half of Gordon's question, but maybe I've worked it out now. So you talk about the K-mesons, but what about the other parity? I mean, what are we supposed to think about the other parity violating experiments, so like Wu and the cobalt? So that seems like a parity violation. Are you saying we can infer time violation, time reversal invariance violation?
Right,
on that
you
as
can
well?
infer my time reversal violation.
Okay.
But that's just CT and ordinary.
Yeah, you can infer,
Which is just-
right, you normally infer this, and this is equals the back, so you can infer that.
So as far as you're concerned, that was sufficient. We didn't need any. I mean,
We didn't need any. I didn't know it.
Well, we already knew that quantum field theory wasn't time reversal
so the
invariant.
standard story is, I mean, people saw the parity experiments and they're like, oh no, time reversal invariance has gone. Oh no, it's okay because we've got CP's conservation and it's somehow the K-mesons that really give you trouble.
Yeah.
But you're saying we don't even need the K-mesons.
No, they say something different according to me. But here's
Which
another.
one is time mason?
Sorry? The original parity violation things are also time violation things. However, if the reason we were worried about that was that we thought it would be really bizarre if there was a fundamental preferred temporal orientation, don't worry. You can't conclude from violation of time reversal invariance that there is a fundamental preferred temporal orientation. You could conclude that from violation of PT. So in the paper that I posted on the conference webpage, I tried to defend the claim that you'd expect to, for the realistic testing, you'd expect to get violation of a PT theorem if you had a representation of temporal orientation. You can get violation of time reversal invariance by having this different thing that usually goes by the name of epsilon, representing total orientation. That thing picks up a sign flip under time reversal invariance, so you could have that, and it's Lorentzian invariant, and thereby explain violation of time reversal invariance.
I'm going to suggest that we take a brief break before the panel. Thanks for your